This is going to work with my rival Kincaid and Shaowei group. It is well known that linear arithmetic over the real and integer is decidable. So if you have a system of linear inequalities on the left hand side, you can interpret the conjunction geometrically as a convex polyhedron on the right hand side. And by linear integer programming, this can be solved. By POPL'23, we can use this to test the satisfiability of all ground formulas. As an application, we can discard verification conditions over linear arithmetic. Beyond decidability, linear arithmetic supports consequence finding. If we have a formula f of some form, we typically want to have a formula g of some form, such that f entails c, and such a g is said to be a consequence of f, and we typically want it to be the best in the sense of logically strongest. For example, if you are trying to compute polyhedral poles, f takes the form of a conjunction of two formulas, a transition formula t over pre-state x and post-state x prime, representing, say, the semantics of an assignment statement, conjoined with ax less than or equals to d, which defines the set of pre-states. And you want to find cd, preferably best, such that f entails cx prime less than or equals to d. So you see over here that the consequence is only over the variables x prime. Or you may want to do polyhedral join. Then f takes the form of a disjunction of two systems of linear inequalities, and you want to find the best c and d, such that f entails cx less than or equals to d. Or you may want to do ranking function synthesis. Then you can encode the body of your loop as a transition formula f over pre-state x and post-state x prime, and you are trying to find a vector c representing the ranking function such that f entails cx prime less than or equal to cx minus 1, conjoined with cx less than at least 0. So the first part tells you that your rank strictly decreases, and the second part tells you that you have a well-founded order. Right, so the parts in green are all instances of consequence finding, and it shows us how that enables applications. On the other hand, nonlinear polynomial arithmetic with integrality constraints is well known to be undecidable. So the applications, like the ones before, discharging VCs, finding poles, join, ranking function synthesis, where in the linear case, we typically have very strong formal guarantees. In the nonlinear case, the claims have to be far weaker. So what we want to do in this work is to improve on this picture by providing a decidable theory of nonlinear arithmetic where strongest consequences of different forms can be computed. We call this theory LIRR, which stands for the theory of linear integer real rings. We give an axiomatization which uses only foreign clauses, so the theory is convex, and we can combine this with other theories via the Nielsen-Alpen protocol. We give an effective model theory based on what we call algebraic cones and lattices, and the model theory being effective allows for decidability. Given a ground formula f, we can decide if it's satisfiable. We show that algebraic cones are closed under several operations, and this in turn leads to consequence finding. Given a ground formula f, we can find strongest consequences of different forms. As immediate applications, we have a numerical abstract domain for nonlinear arithmetic, and we have a monotone invariant generation scheme, where monotone means that whenever a precondition is strengthened, the invariance that we find cannot be worse. So let us start with the axioms. The language of LIRR is the first order language over the signature 0, 1 plus times less than or equal to equality and an unary predicate called int, which you can read as integer. A model consists of a set, typically called a carrier, of elements and interpretations for all constant function and predicate signals. So for example, we can take the set of real numbers as a carrier. We can interpret 0, 1 plus and so on in the usual way. And we can interpret int as a subset of integers. If a model satisfies the LIRR axioms, it is an LIRR model. We have three groups of axioms. The first group are the axioms of commutative rings, and these are completely standard. We have a subset of axioms from linear rational arithmetic, and we have some axioms that characterize what integers are. As I go through the axioms, it is useful to keep the set of real numbers and the subset of integers in mind. You will find that they satisfy all the axioms, and it is what we call the standard model. Commutative ring axioms, 0 and 1 are identities, so for all x, x plus 0 is x, x times 1 is x. Addition and multiplication are associative and commutative, so you can put brackets anywhere you like. You can interchange terms. Additive inverses, for all x that exists y such that x plus y is equal to 0, and we may call such a y negative x. Distributivity, if you have x times y plus z, you can expand it out to x times y plus x times z. From linear rational arithmetic, we have 0 less than or equal to 1, and they are distinct elements. Less than or equals to forms a partial order. This means reflexivity, antisymmetry, and transitivity. Unlike the usual case, this may only be partial. You can have elements x and y in a model that are not related. Less than or equals to is compatible with plus. So if x is less than or equals to y, you can add the same z to both sides. Perforation freeness, if you have 0 less than or equal to n copies of x added together, you can sort of divide by n on both sides to conclude 0 less than or equal to x. We may abbreviate n copies of x added together as nx. I may read it as n times x. And we also let m abbreviate 1 plus 1 summed up n times. Divisibility, for all positive integers n, there exists x such that nx is equal to 1. So if you sort of divide by n on both sides, you see that every model contains an element x that looks like a 1 over n. And at this point, you should see that a set of real numbers satisfies all these axioms. Moving on to the integers, we insist that 1 is an integer, that if x and y are integers, x plus y is an integer. If x is an integer, negative x is an integer. So one way to say this is that the subset of integers within a model forms the subgroup that contains 1. Our last axiom is called the cutting planes axiom. So for all choices of integers m and n strictly greater than 0, we get one axiom that says if nx is less than or equal to n, and int x, meaning that x is an integer, then x is less than or equal to m over n rounded down to the nearest integer. Concretely, for example, if you pick m to be 3, n to be 2, you get one axiom that reads 2x less than or equal to 3, and int x implies x less than or equal to 1, because 3 over 2 rounded down gives you a 1. In other words, the rounding is something that you do yourself, and after you have done that, you get one such axiom. So those are our axioms. What's missing? We don't have the totality of order. We don't have induction for integers. If x times y is equal to 0, it does not mean that x is 0 or y is 0. If x and y are both non-negative, it does not mean that x times y is non-negative. And the list has to go on forever because the theory of integers is not recursively axiomatizable. So it is in this sense that the theory is said to be weak. However, we retain all the power of linear arithmetic in the following sense. Whenever f is ground, negation-free, and multiplication-free, hence linear, it is satisfiable modulo the standard model if and only if it is satisfiable modulo LIRR. And what this means is that problems that can be encoded in linear arithmetic can be encoded in LIRR without losing precision. And this stands in contrast to, say, encoding an integer problem in the theory of reals. So now we have a standard model with the set of real numbers and the subset of integers. We now want to find a family of models that we can compute effectively with. So towards this, we take the following steps. First, by our divisibility axiom, we see that every model contains elements that look like the rationals. So if you fix a finite set of variables x, then our terms start looking like polynomials with rational coefficients. This suggests taking Qx, the ring of rational polynomials, as the carrier, where we interpret every term as itself, the so-called term model, and we represent predicates as subsets of Qx with some structure. Step 2, we show that there are enough representations in the sense that whenever f is satisfiable and has a model, it has a representable one. Thirdly, among the representable models, we identify a subset of finitely generated ones so that we can compute with them. And we show that we don't lose anything. We still have enough models in the same sense. Whenever f is satisfiable and has a model, it has a finitely generated one. And this in turn gives us decidable satisfiability. So step 1, in any model M, we first observe that by our axioms, the subset of positive elements in M form a cone that contains 1. So if P1 and P2 are non-negative, P1 plus P2 is non-negative. If P is non-negative and A is a non-negative scalar, A times P is non-negative. The subset of 0 elements in M forms an ideal. So if Z1 and Z2 are equal to 0, so is their sum. If Z is equal to 0, multiplying that with anything still gives you a 0. And the subset of integer elements in M forms a subgroup that contains 1, as we've mentioned before. Hence, with Qx as the carrier, we can represent less than or equals to equality and int using a pair CL, where C is a cone of polynomials, which you can think of as the cone of positives. L is an additive subgroup of polynomials, and C and L satisfy some closure conditions. For example, C intersect minus C forms an ideal. Then, we can interpret P less than or equals to Q as true if and only if Q minus P is in C. So just bring P over to the other side and test for membership in the cone of positives. We interpret P equals to Q as true if and only if P minus Q and Q minus P are both in C. This is true by anti-symmetry. And we interpret in S as true if and only if S lies in L. So this is how we can use a pair CL to interpret our predicates. We call such a CL regular, and the closure conditions really just tell you that C and L are large enough to be closed under entailment. Formally, we have a theorem that says whenever CL is regular, it represents an LIRR model, which we will denote by M of CL. So now we have representable models. We want to say that we have enough of them. So here's a satisfiability theorem. Let F be a conjunctive formula, which we can write in 3 parts. The first part consists of a set of inequalities, saying that some polynomial terms P are non-negative. The second part consists of some integer constraints, saying that some polynomial terms S are integers. And the third part consists of negative literals. Let CL be the least regular pair, such that P is contained in C and S is contained in L. Then F is satisfiable if and only if M of CL satisfies F. So we have enough representable models. As an observation, if you look at the containment relations P subset C and S subset L, then it tells you that C and L contains constraints that come from the formula. And regular really means closure under entailment. So C is really the set of consequences of positive literals. And since our axioms are all Horn clauses, the negative literals do not generate any consequences. So C is really the set of consequences of the entire formula F. And informally for now, we will call this the consequence cone. By step 3, among the representable models, we now want to pick out a subset of finitely generated ones so that we can compute with them. Define C to be an algebraic cone if there exist finite sets Z and P, such that C is equal to the smallest ideal containing Z plus the smallest cone containing P. Equivalently, the ideal generated by Z plus the cone generated by P. The plus over here just means that any element in C can be returned as an F plus G, where F comes from the first part and G comes from the second part. Likewise, we define L to be an algebraic lattice if there exist finite sets Z and D, such that L is equal to the ideal generated by Z plus the subgroup generated by D. And we will call the pair CL algebraic if the two Z's happen to be the same. So now we have finite representations, but they may not actually represent models yet because they may not be regular, they may not be large enough. So here's a theorem to the rescue. If CL is algebraic, the least regular C prime L prime that contains CL exists, is algebraic, and can be computed. This is what we call the regular closure of CL. So the key idea behind the proof is that our choice of C, allowing us to decompose it into an ideal plus a cone, means that we can apply ring theory to the ideal part, and we can apply polyhedral theory and algorithms to the cone part. And by combining procedures from 2 domains, we are able to compute the regular closure. And our choice of representation of C, allowing us to write it as an ideal and a cone, is really the essence of why algebraic cones can be manipulated effectively in general. So now we have finitely generated representations using algebraic and regular cones, regular CL. We want to again say that we have enough of them, and here's an effective satisfiability theorem. Let F be a conjunctive formula written as before. Let CL be the regular closure of the algebraic cone generated by TS. So the same inclusion conditions as before, but now we can compute CL. Then F is satisfiable if and only if M of CL satisfies F. So we have enough finitely generated representation. Since everything here is computable, this means that the consequence cone C of a conjunctive formula F can be computed. And because of DP-LLP, we can leave this to test satisfiability of all ground formulas. So at this point, we have a theory solver. You may wonder if it actually works for general satisfiability tasks modulo the standard theory of integers. So we ran benchmarks from SNP comps, QFNRA, and QFNIA. The short answer is that it's not great. So firstly, LIRR is not really suitable for satisfiability because the models are not even numbers anyway. And on the unset task, you can see the numbers in blue are those for our tool, it's called Kylon. And it proves 6 out of 40 tasks for unset and 14 for NRA and 14 tasks out of 41 for NIA. And these numbers are small in comparison to the numbers for the other solvers. So a key reason is that LIRR admits too many models. On the other hand, our target application is really program analysis and verification, and the formulas that arise in that domain can be quite different. Right, moving on to effective closure, we now want to say that the algebraic cones are closed under several operations, and this enables finding strongest consequences of certain forms. The first operation is projection. If C is an algebraic cone in Qx, and Y is a subset of X, then C intersect Qy is an algebraic cone. If you think of an algebraic cone as a set of constraints generalizing linear inequalities, then in a very, very, very loose sense, you can think of them as defining a convex polyhedron in some high-dimensional space, say spanned by x's, x squared, and y squared. To take this intersection corresponds to taking the projection of the polyhedron onto x's that involve only variables y. Second operation is intersection. If C1 and C2 are algebraic cones, the intersection is. This corresponds geometrically to taking the convex hull of polyhedra, and this gives us an abstract joint. Closure under sum. If C1 and C2 are algebraic cones, so is their sum. This corresponds geometrically to the intersection of polyhedra. This gives us an abstract meet, and now with all these operations, we have a numerical abstract domain. We also have closure under other operations like inverse ring homomorphism and linear restriction, which I'll talk about on the next slide. So with effective closure, we can compute the consequence cone of F, defined formally as the set of polynomials P, such that F entails P to be non-negative. And we'll denote this by C of F. So by consequence here, we really mean inequalities that are implied by F. When F is conjunctive, this CF is really just the consequence cone that I mentioned before. And by effective satisfiability, we already know that it is algebraic and computable. Effective closure lets us extend these to general formulas and to compute consequences of different forms. For example, intersection, CF intersect QY gives us the set of all consequences of F, where we existentially quantify out variables that are not in Y. If you take the intersection of two consequence cones, you get the consequences of a disjunctive formula. And if you take the sum of two consequence cones, it gives you the consequences of a conjunctive formula. If you have inverse ring homomorphism and linear restriction, we are able to extract the set of all consequences that are polynomial in some variables and linear in others. And by combining these things, we have a monotone invariant generation scheme as follows. If you have a loop body, you can encode it as a transition formula F over pre-state X and post-state X prime, and you extract the following from the consequence cone of F. First, the set of all linear invariant polynomials. So these are linear polynomials P, such that F entails P prime to be equal to P. In other words, polynomial terms whose values do not change across iterations of a loop. Then we extract all recurrences of the form x prime less than or equal to x plus P, where P is polynomially generated by the linear invariant polynomials. And once we have x prime less than or equal to x plus P, since P is a polynomial whose value doesn't change across iterations, then for k iterations, you have x prime less than or equal to x plus kp. And by quantifying over k existentially, you get a loop summary. So monotonicity is ensured here because whenever we do consequence finding, we are always extracting all consequences of the desired forms. Alright, so on to experimental results. Now that we can extract nonlinear invariants, we want to know if they are actually useful for program verification. So we ran benchmarks from FE-Com's C program, which safety loops. We had 178 tasks for linear, 290 tasks for nonlinear. The tool is called pylon, and we added a refine heuristic to get pylon plus refine. And because of monotonicity, we can be sure that the results for this tool will not be worse. So here are the results. The numbers in blue are the ones for the tool. The numbers in black are the ones that are the best in each category. So you can see over here that for the linear category, pylon if doesn't do as well as the best, but after adding the refined heuristic, it is very competitive. And in the nonlinear category, pylon inf and pylon plus refine are already the best in that category. Right, so that ends my talk. I'm ready for questions.
Okay, thanks a lot.
So you considered using it in or you tried it in a SMT solver sort of situation, and it didn't solve as much as the more general solvers. Have you considered using it with some kind of CGAR setup as a first pass, and then in conjunction with a stronger solver?
No, we haven't tried that. I can't be sure I can answer you in terms of like whether it would actually be helpful or not. But
I have a question. There's a theory on C-finite recurrences where you restrict your syntax such that, let's say, the assignments in the loop body, right? The right-hand side are polynomials, but the variables in the loop in the body are basically ordered. So if you are, let's say, line K, you can only refer on the right-hand side to all the variables that you have assigned before. The advantage is that you can capture the let's say, behavior as a kind of a C-finite recurrence that has a closed form solution. Does that type of theory fall within, let's say, your framework here? Do you happen to know this? Because it's also non-linear.
yeah, I would think you can combine it.
Okay.
But yeah, like the contribution here is a theory, and in terms of the form of the syntax, it's going to be orthogonal to that. So that is my impression anyway. But Zach would probably know better.
Any no further questions? Okay, then I would like to thank the speaker again. Thank you.